Two things we're going to do with our Maduino board during this video. Number one is we're going to learn how to monitor the battery voltage. And the second one is we're going to learn how to send a text message when that battery voltage reaches a low threshold. Here we are on the page where I purchased this Maduino board from. And again, this is a Maduino Zero. It has a SIM7600 module, which you can see in the center here. That allows us to connect to LTE networks, and we can send HTTP requests and get GPS data. But if you scroll down here, you get down to kind of the hardware and their firmware. And if you open this page, you're going to get to a GitHub page where you can find the hardware. I've already downloaded this, and I've loaded this in this tab. So here's that circuit diagram, and it has a lot of different areas of the board. Here's the SIM7600 module and all of its pinouts. And up here in the upper left-hand corner, this is where I want to focus right now. Let me just zoom into this thing a little bit more. So we can see the pinouts for the MCU. And in particular, you can see pins labeled A0, A1, A2, A3, A4, and then here's an A5 pin on this side. Those are 6, so 0 through 5, 6 analog input pins. And so on those 6 pins, there's analog to digital converters. And so you could measure the voltage on those pins using one of those A to D converters. Take a look at this diagram here, and you can see that the battery input voltage is connected to pin A1 through a resistive voltage divider. In the ideal world, if these were both exactly 1 mega ohm resistors, then the voltage input to pin A1 will be exactly 1/2 of the battery voltage. There is some tolerance on these resistors. They spec them out for low tolerance, 1%, to kind of maintain that this is roughly about 1/2 of the battery input voltage. So the battery code uses one of the analog to digital converters as part of the Maduino board. So let's take a look at what that means and kind of the theory of analog and digital conversion. First of all, let's define what analog means and what digital means. Analog generally means that the voltage and the currents are varying continuously with time. And so you get values that, aren't discrete values. They're not like 1 or 0 or 5 or 0 or, anything like that. They can range from, 1.1 to 1.22 or whatever they are. Physically, phenomena that happen in our environment like sound and temperature and pressure are represented by analog signals. And we use transducers, in the analog world, we use something, like a microphone to convert sound waves to voltage that varies continuously. So it's an analog signal. So let's take a look at digital signals. Digital signals typically have 2 states. There's an on state and an off state. A 0 or a 1 is typically how we think about these. Physically, if you were to measure what a 1 state is, in this particular diagram, it's something around 5 volts. And the 0 state is something around 0 volts. And so the voltage typically is kind of varying between 2 different states. So in the real world, you won't see such square waves, waves with such, right angles. Noise and bandwidth constraints typically limit the frequencies that you can send down, certain, like a transmission line or something. And so a lot of times these signals are rounded off. But for our purposes in this discussion, we're going to assume the ideal case. So we have either a 1 or a 0. We have binary states, and we have these things called bits. And when you combine 8 bits, if you take 8 bits and you smash them together, that's called a byte. And so when you hear terms like, hey, there's a byte of data, that's really 8 bits. And then, that's the land where computers and networking really work is, they take a look at bytes or bits and either sending them or process them or doing a bunch of logic around them. So in the next slide, we're going to take a look at converting analog signals to digital signals. And so there's really 3 steps to converting analog to digital. What we're going to do is we're going to look at this kind of high-level circuit diagram of this analog to digital converter. This is a 2-bit analog to digital converter. The 2-bit refers to how many bits are on the output. There's 2 bits on the output. So in general, n bits can represent 2 to the nth number of levels or states or values, right? So this 2-bit case can represent 2 to the 2, which is 4, and you can see those over here, and we'll get to them in a second. But if we look back on the left-hand side, there is a voltage divider tree on the left-hand side that takes some reference voltage. In the Maduino case, this reference voltage is 3.3 volts. And on this ideal voltage divider tree, there's 4 resistors dividing, dropping a quarter of that voltage. And so this node is a quarter, this is half, that's 3/4 of the reference voltage. The second step on converting analog to digital is now we have a comparator. And so each of these comparators has the source as one of its inputs. That's on the positive node. And on the negative node, we get one of the values from the tree. And how each individual comparator works is if the voltage on the positive node is greater than the voltage on the negative node, then the output of the comparator is high, or let's call it a 1. So in this particular comparator, the output is high, so it's a 1, if the source voltage is larger than a quarter of the reference voltage. This particular comparator is the same thing, but only it goes high if it's larger than half the reference voltage. And then finally, this third comparator, the output of this only goes high if the input voltage is higher than 3/4 of the reference voltage. At the output of the comparators, we've already kind of quantized the different levels that we have. And so there are 4 levels, and you can see the quantization here. So anything from 0 to less than a quarter of the reference voltage, all of these comparator outputs are 0. And as soon as we go above a quarter of the reference, but less than half, the first comparator goes high. And C0 is just a feed through from the ground, so that's always low. You'll see that. But the output of the first comparator is always high once you are larger than a quarter of the reference. The output of the second comparator is always high once you're larger than half the reference, and the output of the third comparator is high once you're larger than 3/4 of the reference. So you can see here we've already kind of quantized the analog signal into 4 different states. Now this really isn't our binary state. I mean, we talked about how we have 2 bits, but now there's an encoder process that takes these 4 states and encodes them into our 2-bit output. So you can imagine as you scale to, say, 10 bits, you have 2 to the 10th resistors and 2 to the 10th minus 1 comparators. But thanks to the modern semiconductor engineering, you can fit that into a very small space. So let's dive into some code. For the battery monitor, I've created a new C++ class. And let's take a look at the definition of this class first. So you can see the new class name is called battery. So in the constructor, you'll see it takes 3 inputs. It takes what the 0% voltage is, and we'll see this applied in the formula, but essentially when the voltage hits this level or this value, then the output is computed as 0%. The second parameter for the constructor is the max voltage. And so for the battery that we're using, the max voltage is around 4.2 volts, and we'll see that. And then there's a third parameter, which is the low battery mode percent. So you can imagine that at some point you want to know when this battery has entered its low battery mode. And so this is the threshold. So let's say you set it to 30%. So if below 30%, the battery's in its low battery mode state. After the constructor, we'll see a refresh method. And we'll get to the details of that in a little bit, but that's the public method that you call when you want to refresh the measurement of the battery state. The next 3 are simply inline functions that return private variables. So this private variable millis is returned through this inline function and so on down here. And we'll talk about these in a little bit, but you can start to get an idea that there's an analog to digital value. That value is converted to a voltage, and we use that voltage to compute some current percent. Here's another inline function, and there's a little bit of logic here, but not much, so it's just inlined. If the current percent is less than this low battery mode percent, then the battery is in low battery mode. And finally, the last three public functions here are just some helpers to convert the data to string values. Let's look at the private properties and the private members down here. So the top three simply capture the constructor parameters, and we'll see that when we look at the details of the constructor. The next four hold the values every single time we collect a new measurement. And there's two private methods down here that actually do the work when you actually use the public refresh. So let's take a look at the code. Now we can see there that the constructor, we talked about this already, there's three parameters, and those three parameters are used to initialize the three corresponding private member variables. And there's a little bit of setup. So here we're setting the resolution of the analog to digital converter. The default, as you can see, is 10 bits, but we're setting it to 12. And so the output can have values of 2 to the 12th different levels, which is 4096. And so the output, so when we actually get the number out of the analog to digital converter, it'll range between values between 0 and 4095. And that'll be important later on when we take these values and we want to convert them to a voltage. And then finally on the constructor, we automatically call refresh. So we're automatically setting or sampling the analog to digital converter and getting our initial value set. And we'll look at this function in a little bit. Next are the three string helpers. And we use these in kind of different areas. And so I just kind of encapsulated this functionality into this area. So just taking whatever the current values are, and there's three different string representations depending on what you're trying to do. And so there's a CSV representation, there's just a plain string representation, and this data, we're actually going to upload this to as part of our HTTP post package. And so there's an HTTP post representation. So let's look at this refresh method. This is called in the constructor. It can also be called, it's a public method, so it can also be called anytime during your code. And then there's three things it does. The first thing it does is it samples the current time. So how long has the board been running in milliseconds? And then it calls this function sample analog to digital converter. And so that's a private member down here. We'll look at the details of that. And then it calls a compute percent method. And both these are private methods. They can't be called outside of this class. So let's take a look at these private methods. So let's talk about the sample analog to digital converter function here. And so this is where we're actually sampling the pin A1. We're using the analog to digital converter inside the Arduino to sample the voltage that's on pin A1, and we're getting the output value. And the value that we're getting out is actually one of the different levels. And we set this to 12-bit mode. And so we can get levels or numbers between 0 and 4095 out of this analog digital converter. We're sampling pin A1 because that's the pin that's connected to our battery through our resistive voltage divider. Ideally, this is about half the battery voltage. And so the values that we get out here, they range from 0 to 4095. 0 will correspond to 0 volts, and 4095 is going to correspond to our analog to digital converter reference voltage, which is 3.3 volts in this case. If we were going to compute this analog to digital converter value, this is the formula for it. So here's the value for the voltage at pin A1. And then to convert it, we multiply this by the number of levels and divide by the reference voltage. And just a quick check, if this value is 0, we get 0 out. If this value is 3.3, so if half the battery voltage is 3.3, then those 3.3s are going to cancel and you're going to get 4095 out. So that checks. This is the formula to compute this. So we don't have to use this formula to compute the analog to digital converter value. All right, we're going to be given this value, but what we want to do is we want to use this formula and invert it to something where we can compute the battery voltage. given the analog to digital converter value. So here's this inversion, and this inversion is directly from here, and you can see it in code down here on line 67. And the only difference is between line 52 and 67 is I pulled out some of these things into variables. So this factor corresponds to the 2, and it's not quite 2. We'll talk about that in a second. Here's the analog to digital converter value. This is the reference voltage value, and I've set that to 3.3. And here's the number of levels, and I set that to 4,095. Now let's come back to this. This is the only thing that's quite a little bit different. This is 1.98436. I took the time. I wanted to make sure that everything was corresponded exactly to what I thought it was going to be. And so I took my multimeter and I measured the battery voltage when the analog to digital converter told me the value was 2,426. And so if I use this, I can compute, I now know the battery voltage, and I know the analog to digital converter value, and I can compute a factor here instead of 2. When I compute that factor, it's not quite 2, it's 1.984636. And again, it's not exactly 2 because those resistors have a 1% tolerance. And so what we're seeing here is the result of this 1% tolerance. But because every Maduino board is going to have different resistors in there, and the tolerance is still 1%, but this number is going to vary between something a little bit less than 1, which is what I have, to something just a little bit larger than 1. And so the most generic case, I would set this to a factor of 2, and I would ignore kind of the differences that each board provides us. So then down here on line 67, when we sample, we convert that analog to digital current value to an actual voltage. This is the battery voltage at the time that we sampled. All right, let's talk about this computed percentage function here. On line 87, we're actually compute the percent. And as inputs to this equation, we take the current voltage, which we sampled using our previous method, and we get that voltage. And then we're using our 2 input parameters here, which are the 0% voltage and the max voltage. Max voltage is related to our battery pack. I'm using this LP603449. This is roughly a 4.2 max voltage battery pack. And so that's the number I'm putting in here. I actually measured this. I fully charged the battery pack, and I measured the voltage when the battery was connected up to the Maduino. So when it's sampling 100%, I measured that voltage, and I got the value of 4.2. And the other experiment that I did is I measured the value that when the board cut off. And so I got a value of roughly 2,044 as our analog to digital converter value. And if you use our formula, you can compute that that's roughly a voltage of 3.26 volts. We're actually providing in the 0 voltage point and the max voltage as part of our constructor. And then we use the current voltage as our measured value, and we use that to convert it to a percentage. And then lines 89 through 96 are just clamping it. So if you compute a percentage less than 0, just clamp it to 0. If something's greater than 100, just clamp it to 100. So now that we've got that battery monitor class created, I set up my code so that I would sample the battery voltage every 10 minutes and upload it as part of the package that we send to our API endpoint here. So you can see, this sampling was at 8:06 and this one at 8:16, so roughly about 10 minutes in between samples. I started it all the way down here at about 4:18 on March 17th, and the battery was, I just unplugged it, so it read 99.99%, and that's the percent. The other information that I'm setting up with every API post is the milliseconds. So that's the how long the board's been running at the time that we sampled the battery voltage. Here's actually the analog to digital converter value. This is the actual voltage that we computed using our function. And then this is the computed percentage that we use of that function. And I let this run. Again, every 10 minutes, it ran for a little over a day. It ended the next morning at 8:30, and we're at 0%. I put all that information in a spreadsheet, and that's checked into the Git repo. And so you can use the power consumption, and we're going to look at that spreadsheet next. So this first column is how long the board was running at the time when we took the sample. Column C is the actual analog to digital conversion value, so some number between 0 and 4095. D is our value that we computed using our class for voltage, and E is the value that we computed using our class for percentage. This other column, column B, is a transformation of column A. I just computed the number of minutes since our first sample, which is this value here. So this is 10 minutes, 20 minutes, 30 minutes, 40 minutes. So every 10 minutes roughly we're getting a new point. So here are the charts of these numbers, and here's the analog to digital converter value. Here's the voltage and the percentage. And you can see the analog digital converter value. The left-hand side is when the battery's at 100% and we're functioning, and then we're sampling every 10 minutes, we get another point. Over on the right-hand side, we get the last point and then the board turned off. So it's no longer functioning. And so using the right-hand side, this is where you can find the 0-point voltage value. So what's the value of the voltage for 0%? This is the value of the voltage you can feed in the constructor for the battery class, and that's their 0% voltage over on this side. So when the battery turns off, you can see that there's still voltage. There's about 3.3 volts roughly still in the battery pack, but it's not enough to run the board anymore. So that's our 0% voltage. And so after I did that once, I reran this, and then I computed the percentage. And you can see it goes from 100% down to 0% because we've kind of calibrated it using this as our 0% voltage, and this is our max voltage. And we feed those into the constructors of our class at this point. So once you have this calibrated, then it's pretty accurate. And you can see it went down to 0, and at some point it was 0 and the board turned off. One of the things that you do notice here at the end, it's pretty linear, kind of stay close to the line, but you can see definitely at the end, once you get to about here, it just falls down pretty quick. All right, and the other bit of new code is the SMS code. And again, the idea is that at some point we want to use the SIM7600 module and send a text message to a number. So this SMS class is a little simpler than our battery class. We should be able to get to this pretty quickly. So the constructor takes a reference to the command helper as the parameter, and then there's only one public method on here, which is the send, and that takes two parameters, a number and a message. And we'll see that in a second how that works out. If we look at the implementation of this, here again is the constructor, our single parameter by reference. We're using that to set our private member variable to initialize that. And then here's the send method. So I did put a note here. So the Twilio Super SIM card doesn't really allow you to send text messages to phone numbers. When you send a text message using the commands below, we'll go through these commands, but when you send a text message, what you really are doing is you're sending it back to Twilio's API, and then Twilio takes that and forwards that over to your webhook. And so I configured it so that it would just send it right to the same webhook I've been using for HTTP. And so really, in this, if you're using the Twilio Super SIM card, this is no different than just using the HTTP helper class and posting data to our webhook. If you're using a different SIM card, then this should actually send a text message to your phone number. So here's the commands that you can use. If you want to debug, you can start the verbose, and essentially this sets a debug flag to true, and then you can see all the outputs of these commands. We're using our command helper, and again, we reviewed this in a previous class, but this command helper sends AT commands over to the SIM7600 module through that serial port that we have connected to it. And so this first AT command is setting the SMS mode to text. The values here are either a 0 or a 1. 0 is what they call PDU, which look more like a binary format, and 1 is their text mode. The second command that you can see here is the AT plus. It's a CMGS command. And in that command, we actually provide a phone number that we want the text message to be sent to. And the third command is your actual message. You're sending your actual data over. And so that's provided as a parameter here. So you send the message. There's a carriage return. And then here's a special hex character 1A. And so that's, I think it's Control R. So if you're on a keypad, you can type Control R, but that hex code ends the command and actually sends the text message. So that's it for this class. It's really pretty simple. But again, for the Twilio Super SIM card that I'm using, this is no different than just sending the data over through HTTP. So finally, let's take a look at the last bit of code change that's happened here. If we look at our main CPP class, you can see at the very top here I've included both the battery and the SMS header so we can use them in the file. So here's where I create an instance of the battery class. And again, I provided the 3 parameters. And just a quick review on what those parameters are. That's the 0% voltage, the max voltage, and the low battery mode percent. And the values I'm providing are 3.3 for the 0% voltage, 4.2 for the max voltage, and 30% for this low battery mode percent. And how that's used is if you call this function is low battery mode, it'll return true if the current percentage is below that threshold. Here's where I create an instance of the SMS class, and it just took the command helper by reference. And so one more slight difference is I added a new file to the SD card. So as I'm sampling the battery, I wanted to save those so I could create that plot that you've already seen. And so here's the battery data file. So down here in the setup, which is run once, towards the bottom here, you can see I'm actually printing all the lines of data that's in that file. So I would run for a while, and then I would start it up, and I would see all the lines. I could copy and paste them into an Excel sheet. Let's take a look at the main loop here. At the very top, one of the first things I do is I refresh the battery data. So I'm sampling the analog to digital converter for that pin. I now have computed the new voltage and the new percentage. I save some of that data to the SD card, and I also serialize out it to the console out. So essentially I'm printing this. If you're hooked up to the console and you're watching on the serial monitor, you can see what the current battery values are. Once I've sampled and saved and printed it out, then I can start to use that data. So here's some code where I've implemented some low power options. So for example, I'm using my function is low battery mode. So if I'm in low battery mode, what I can do here is I can modulate and change the GPS refresh period. So again, that's how often I'm sampling the GPS. And so if I'm in low battery mode, I can sample less often and maybe enter like a conservation state. So I'm not going to sample at my high rate because I'm in my low battery mode. So if we look at the top, I've defined these two as constants. So we'll go up here at the very top and just look at them real quick. So here's the GPS refresh period for low battery mode. It's set to 3,600 seconds, which is an hour. And then the default sampling rate is every 600 seconds, which is every 10 minutes. So I went from 10 minutes to every 60 minutes, right? So if I'm in the low battery mode, then I'm sampling once every hour. Otherwise, I'm sampling more often, which is once every 10 minutes. Here's some more code for when I enter low battery mode. There is a variable here that I initialize right before. So once you power the board on, this is initialized to false. And so what we're seeing here is a little bit more code for the low battery mode. So if I'm in low battery mode and this variable is set to false, right, then I'm going to do this. I'm going to send an SMS that this board is switched to low power mode. Come find me and swap out my batteries. You can do whatever you want here, but this is just an example. And again, this SMS, it doesn't matter where I send this to. For the Twilio Super SIM card, it's not going to go to a real phone number. It's going to go to our endpoint. So you set it to 000, it'll go to that endpoint. And then I'm setting that value to true. So I don't send this every single time that I do a loop because I'll be in low battery mode. Theoretically, once I hit low battery mode and I've gone far enough into it, I'm going to be low battery mode all the time. So I don't want to send this SMS every time, but the first time I enter it, then I do want to send this SMS. And so that's some special code that you can enter, using the battery class and also the SMS class. And then everything else in the file is pretty much the same. Again, just a reminder, here's where we actually sample the GPS coordinates. So the only thing that's changed in our posting code, or HTTP post, is the content we're sending up. So now, not only are we including what we used to include before, but we're including a little bit of data from the battery class. And again, that's the analog to digital converter value, that computed voltage and computed percentage. And then we're sending that to the URL as part of our package. And then finally, at the very bottom, there's some slight modifications. And again, here I'm using my battery class. If I'm sampling the GPS and the GPS period is less than 120 seconds, so if it's 2 minutes or less, let's say, then, and my battery is not in the low battery mode, then I'm going to do just this simple delay. I'm going to keep the SIM7600 module on. I'm not going to shut it off to conserve power. I'm just going to do this simple delay. And as we talked about in the last episode, this really is the best option if your GPS collection rates are less than about 2 minutes. Otherwise, we're going to set the module, we're going to turn the module off, and we're going to kind of set us in the lowest power consumption state of the MCU. So we're really conserving power when we're sleeping. We're getting into this lowest power state, and then we turn everything back on and we do our sample, and then we just keep repeating that. So that's it for the changes to the main CPP class. That brings us to the end of this episode. If you have any questions, feel free to comment below. Otherwise, subscribe for more content like this.